Okay, so here's part 2 of the RC circuit lecture. This is the final lecture for chapter 26, and it therefore completes this unit, chapters 24 through 26. I will be posting directions for the take-home exam. It will be a timed exam on Monday of next week, so watch for that very carefully. The instructions will be there before the exam itself, but the exam itself will be administered on Monday. I'm not going to do any example problems here associated with the RC circuit, by the way, because you need to know how to derive the expressions by setting up and solving the differential equations first and foremost, and then any calculations that you would have to perform after that are usually just plug and chug calculations. The most important thing to know, however, is how to derive the expressions. So take a look once again at part 1's lecture and make sure that you understand how to derive the charge across the capacitor as a function of time as it's charging up. Okay, part 2 of the RC circuit has to do with what happens when you discharge a capacitor. So recall the demonstration that I did for you at the beginning of chapter 24 when I discharged the capacitor after unhooking my battery and I discharged my blue capacitor through an electric motor. That's basically the situation here. So we begin with an already charged up capacitor and we then just discharge it through a resistor. No battery is present. Okay, so right here is my capacitor. It has capacitance C, and it initially has a charge, positive Q naught as it's referred to, on one plate, and then the negative on the other plate. Okay, and then right here is a resistor with resistance R. And then you flip a switch or something like that, and then ultimately the capacitor starts to discharge. Okay, we once again just use loop rule in order to set up this expression. I'm going to start here and then go this way like so across my circuit, ending up back where I started, so then therefore the total potential difference is 0. So first of all, go across the capacitor from low to high potential, so then therefore when you do final minus initial, the voltage is going to be a positive number. That's going to be Q over C. Okay, and then we go with the conventional current here across the resistor. We fall from high to low potential, so then therefore Ohm's law is I times R, but the potential difference is negative. And then we set it equal to 0. Okay, now here's something that you have to remember. The current I. The current I has to be written as a negative. The reason why is because the capacitor is discharging with respect to time. Because it's discharging with respect to time, the change in charge on the capacitor with respect to time is a negative number for that reason. This is really easy to forget. So make sure that you write the I here as a negative dq dt. Okay, let's go ahead and replace it here. Like so, and then we'll just separate variables to solve this differential equation, which as you'll see is really easy to do. Okay, first of all, I'm going to divide by R to each, or divide by R rather. Let's just go ahead and do that, like so. Okay, and then let's move this guy here to the other side. Okay, like so. Okay, and now I'm going to go ahead and separate out my variables. So to do so, I'm going to move the dt over here to the right. And then this stuff I'm going to cross multiply over to the left. Like so. And now we integrate. Now when we integrate on the right hand side, we're integrating over time from 0 to t. But now over here on the other side of the expression, we're integrating from the initial value of the charge Q naught on the capacitor's plates to a final value that I'm just going to refer to as Q. And then we're going to solve for Q as a function of time. Okay, so on the right-hand side of the expression, we just first of all end up with time t. And then let's go ahead and integrate here on the left-hand side, and when you do, you just end up with a natural logarithm. So this guy over here on the left-hand side is going to be, first of all, minus RC, and then natural log of Q, where we then have our limits from Q naught to Q, like so. So go ahead and plug in the limits. When I do, I'm also going to move the minus RC down to the denominator on the other side of the expression. Like so. And then let's go ahead and get rid of the natural logarithm. So e to the minus t over RC like so equals then Q over Q naught. And now you just solve for Q. This is the charge on the capacitor still as a function of time. That's this expression here. Okay, and then from that, we can find the voltage across the capacitor as a function of time. Okay, the voltage across the capacitor as a function of time is just going to be this quantity here and then divided by the capacitance C. All right, so the voltage across the capacitor as a function of time is this guy here divided by C. Like so. And then therefore, sometimes you'll maybe asked to graph this function out or identify it in a multiple choice problem or something like that. So if we graph out the voltage across the capacitor now as a function of time, at times t is equal to 0, you have e to the 0th power here, so the initial voltage across the capacitor is just Q naught over C. Like so. All right, then we undergo an exponential decay here, like so, as time goes on. Okay, once we have the charge on the capacitor as a function of time, or equivalently the voltage on the capacitor as a function of time, then we can calculate out a bunch of other things if necessary. So for example, we can find the current flowing through the circuit as a function of time, but when we do, just make sure that you take the negative derivative, like so, as I indicated earlier. Once again, it's really easy to forget that negative sign. If we wanted to, we could also calculate the potential energy as a function of time across the capacitor still as it discharges. That would be, once again, 1/2 Q squared over C, like so. So you have to know how to set up and solve this differential equation here in part 2 of this lecture, and also in part 1 from the earlier lecture as well, to derive the expressions. After that, however, it's usually just a plug and chug sort of situation, and nothing more than that. One thing that I do want to briefly mention, however, before I conclude chapter 26, is specifically this quantity right here in the exponent. Okay, the exponent itself has no units. So then therefore, if you have time in the numerator of the exponent, say time in seconds, what do the units of RC have to be? They also have to be seconds. RC is given a name. It's referred to as the time constant, and we use the Greek letter tau to describe it. Here's how the units of the time constant work. We have, first of all, resistance, which is in terms of ohms, and then multiplied by capacitance, which is in terms of farads. Okay, now from Ohm's law, an ohm is a volt per amp, like so. And then capacitance, remember, comes from the following expression: charge equals capacitance times voltage, like so. So the capacitance then would be Coulomb per volt, like so. Notice that the volts cancel out here and here, and then right down here is an ampere, which is a Coulomb per second. So in the numerator, we have this Coulomb here, and then we divide by coulombs per second. Coulombs cancels out, and you then therefore end up with a time in terms of seconds. So the units of RC, sometimes called the time constant, is in terms of seconds. You might encounter a question like that, for example, in the multiple choice section of the AP exam. Okay, so that does now conclude for us chapter 26 and part 2 of today's lecture. Today's shirt is the sword.
See ya. Stay safe.